All right, hello, my name is Stephen Connaughton. I work in CRANN with the School of Physics for Wojciech Kristich, and the title of my talk, slightly different to advertised, is From Transistors to Memristors, Sub 10 nanometer germanium nanowires. So the first question to answer is, what is a nanowire? And we can consider a nanowire to be basically just like an ordinary wire, except that the diameter is less than 100 nanometers, where a nanometer is 1/1000th of a meter. Now, our wires are actually significantly smaller than that. They tend to be less than 10 nanometers. And in fact, if you look at this one on the screen, it's only 8 nanometers in diameter. Now, what you're actually looking at here, these rows are individual rows of germanium atoms. Germanium is the element from which our wires are made of, and it's a semiconducting material. So you can actually count up the rows here. See that this wire is only 26 atoms across, which is really, really small, even for a nanowire. So when we get these nanowires, we want to make devices out of them. We make it in the following way. We take the wires and we put them on a substrate like this. So you can see the wire is this little line here that you can see. And then on top of that, we put 2 metal electrodes. Now, when you have this configuration with metal electrodes and semiconductor, what you essentially have is a transistor. And transistors are the basis of all modern electronics, in your computers, your iPods, your iPhones, everything. So what we can do is then put a voltage across these 2 metal electrodes that measure the current that flows through our germanium nanowire. So most of you are probably familiar with, or at least have heard of, resistor, inductor, and capacitor. But what you may not know is there is, in fact, a 4th basic circuit element, which is called a memristor. This was proposed by a man named Leon Chua in 1971. Based basically on a symmetry argument. And it was first reported to exist in 2008. And it wasn't seen for so long because you need to make your devices really quite small for it to become important. So a memristor is closely related to a resistor. Now, a resistor does exactly what it says on the tin. It resists the flow of electric current. And a memristor is quite similar. It also resists the flow of electric current. But the difference is that the amount by which it resists the flow will change over time. And more specifically, the memristor remembers how much current has flowed through it in the past, and it will change its resistance accordingly. That's where it gets its name from. It's a memory resistor, a memristor. So in the lab, we see them as these rather fetching graphs here, which look nothing like your typical transistor curves. Now, they're called a pinched hysteresis loop. The reason is that hysteresis refers to the fact that you have these loops, that you can have 2 different currents for one given voltage, and pinched refers to the fact that it goes through one single point. Now, these things are useful. They can be used in non-volatile memory, which is memory which basically doesn't lose its information when you turn off the power. And Hewlett-Packard, who created the first memristor, say that this should be on the market within the next few years. And they can also be used in things called neuromorphic circuits, which are circuits which, in some sense, mimic the action of a brain. Now, everything we've talked about so far has been based on the electric charge. These are all charge-based devices, but the actual effect that we hope to see and hope to investigate is actually based on another property of the electron, which is known as spin. So essentially, with every electron, there's associated a little bit of angular momentum, and this angular momentum has a direction. And for the electron, it can only point in one of 2 directions, and we call this spin up or spin down. Now, for any given electron, we can imagine that its choice of being either spin up or spin down is essentially random. It's like flipping a coin. So if we have 10 electrons, what we would expect is that we see 5 up and 5 down. But something interesting happens when we confine the electrons to one dimension, and we can consider our wires to be well, basically, in one dimension, which we can consider our wires to be, because they can only go forward and backwards, not up or down, left or right, is we see that the spins actually align. And this is what we hope to investigate in our wires in the future. Thank you very much. Oops.